In this video, we're going to talk about the surface energy balance. And this is a very useful tool that starts with the radiative balance of our planet and looks at it explicitly in terms of the surface itself. The surface energy balance is a valuable tool for understanding how changes in surface characteristics are influential on the development of different types of weather phenomena, and when sustained, has an impact on the climate of a given location as well. You would have encountered a very similar schematic to this one that depicts the global radiative balance of the Earth. If you were looking at what these values were in this figure for a particular location such as Canberra, they would look very different again. So it's worth remembering that there's a difference between looking at things globally compared to locally. Over time, our observation methods have become more advanced and we've been able to reduce the uncertainty associated with our understanding of the radiative balance. Cloud cover is a really important part of understanding how much radiation is actually reaching the surface and how much is able to leave our planetary system. So we'll start with the shortwave radiation. Outside of the climate system, the energy coming from the sun as shortwave radiation is the solar constant, which I'll refer to as S-const, although you may already know it from Andy's lectures as L star. Now, because of the presence of an atmosphere, some of that radiation is either reflected by cloud cover or aerosols, or it's absorbed within the atmosphere. So what actually reaches the surface, which I refer to as the global incoming shortwave radiation SG, is a lot smaller than the solar constant reaching the top of the atmosphere. Once it reaches the surface, some of that radiation is reflected and some of it is absorbed, where the proportion that is reflected is a function of the reflectivity of the surface, which we refer to as the albedo, denoted as this alpha symbol. If you integrate across the whole planet, it has a planetary albedo of about 0.3. Some of this material is of course recap from earlier videos in the course, but what's really critical for understanding the surface energy balance is that across individual surface types, the albedo can vary considerably, and this does have an impact on what the surface net shortwave radiation is at any given location. Albedo values are within the range of 0 to 1, and they do vary across surface type. So, for example, if we consider snow, new snow is bright, it's white, it has a high albedo, whereas over time it will get dirty, some of it will melt, and as a consequence of that, the albedo will decrease. For soils, albedo can vary with the soil colour and how wet it is. Across different vegetation types, albedo variations are linked to differences in vegetation traits. So between deciduous and evergreen trees, the albedo range is considered large. Finally, for the built environment, albedo can vary depending upon what type of material we're talking about. So for an asphalt road, it's very black and it has a low albedo, which is why roads are generally hotter than adjacent concrete parts or other structures that are whiter or brighter in their colour and as a consequence have a higher albedo. Moving on to the long wave radiation, we start at the surface where you've already been introduced to the Stefan-Boltzmann equation, which we use to describe the outgoing long wave radiation emitted by the planet. So it's a function of the surface temperature Ts, not the atmospheric air temperature, as well as the emissivity of the surface represented by this epsilon term. Because we have an atmosphere and we have cloud cover, not all of that outgoing long wave radiation leaves the system, where some of it is redirected back down to the surface, which we refer to as the incoming long wave radiation Li. And some of that is also reflected at the surface. So in terms of the net long wave radiation at the surface, each of these three components contribute where the outgoing long wave radiation consists of the emission term and the reflected term. A key trait of all of these is the emissivity, which is the ratio of the actual emission to the blackbody emission. If we integrate across the whole planet, it has an emissivity of approximately 0.6. However, like the albedo, individual surface types can have a different emissivity. Note that for most surfaces, the emissivity has a smaller range than what we saw for the albedo, particularly if we're just considering the range across vegetation and soils. But it is worth noting that some materials do have a much lower emissivity. Now that we have a good understanding of the shortwave and longwave components of the energy balance, we can sum these together to get a quantity called the net radiation. And it really is just that, it's a summation of the shortwave and longwave components. Coming back to the schematic of the radiative balance, we can consider the net radiation at the top of the atmosphere. And this includes the incoming shortwave radiation of 340 watts per metre squared, minus the outgoing shortwave radiation of 100 watts per metre squared. Then for the net longwave radiation, we only have to consider the outgoing component equal to 239 watts per metre squared, as we are above the clouds and therefore have no incoming longwave radiation. Together these terms sum to a value of 1 watt per metre squared, so we have an imbalance at the top of the atmosphere. Moving on to the surface, we can follow similar steps to estimate the net radiation Rn. Again, starting with the shortwave radiation, we have an incoming shortwave component of 185 watts per metre squared, with 24 watts per metre squared reflected at the surface. For the longwave component at the surface, we have cloud cover and therefore have a contribution from the incoming longwave radiation of 342 watts per metre squared and outgoing longwave emission of 398 watts per metre squared. So together these terms give a net radiation of 105 watts per metre squared at the surface. So you'll notice that there's quite a big difference in the net radiation between the top of the atmosphere and the surface. So what's happening here? So what this 105 watts per metre square represents is the net radiative input into the surface. Of course, not all of that energy remains in the surface. Some of that energy is transferred back to the atmosphere, and it can follow one of two pathways. The first one is associated with the latent heat flux. So this is the energy exchange associated with the phase change of water and involves evaporation processes. In this schematic, it has a value of 84 watts per metre squared. The second pathway is the energy exchange associated with the change of temperature, and that's what we refer to as the sensible heat flux. This is heat that you can feel, and it has a value of 20 watts per metre squared. So together there we have an energy exchange back to the atmosphere from the surface of 104 watts per metre squared, which means we have a remaining 1 watt per metre squared imbalance at the surface. So the sensible and latent heat exchange is a consequence of turbulent mixing of air and the resultant heat and moisture transport from the surface to the atmosphere. Some of that turbulence is generated mechanically due to surface friction, which we refer to as forced convection, and that's a characteristic of surface conditions. But turbulence can also occur due to surface heating and buoyancy, which we refer to as free convection. What this schematic is showing us is how wind speed increases with height and that it follows a logarithmic profile, and that the profile changes depending on the surface characteristics. We can describe a friction velocity as a function of the atmospheric stability and the surface roughness. As we move from left to right on this schematic, we go from an aerodynamically rough surface to a smooth surface. And the effect that this has on the wind speed close to the surface is that when there are more complex structures, they exert a larger drag force on the flow and generate more turbulence. This logarithmic wind profile provides a conceptual diagram of how turbulent mixing results in the eddy transfer of momentum to the surface, while heat and moisture are carried away from the surface. Turbulence is easy to observe, so you might recall seeing how the patterns of smoke emitted from a chimney spiral up into the sky, swirling dust, ripples of waves across a lake, or maybe you've experienced it when planes were still flying. But it's very difficult to describe turbulence mathematically. Therefore, we often use bulk formulations to describe the transfer between the surface and the atmosphere at a height z. Therefore, when we talk about the sensible and latent heat fluxes, these are driven by the gradient across these 2 points. The sensible heat flux is a function of the temperature gradient between the surface, represented as Ts, and an arbitrary height in the atmosphere, represented as Ta. The heat transfer is inversely related to the aerodynamic resistance term Ra, which we'll discuss more later, and Cp, the specific heat capacity of air. The sensible heat flux is constrained by the available energy at the surface, which is supplied by solar radiation.
So it peaks during the day and goes to zero at night. However, it can go negative if the atmosphere is warmer than the surface. So the latent heat flux is a function of the moisture gradient between the surface and the atmosphere, which can be calculated by taking the change in the specific humidity. However, it's also common to use the change in the vapour pressure. Here, the latent heat flux is proportional to the difference between the surface specific humidity Qs and the atmospheric specific humidity Qa. It's also inversely proportional to the aerodynamic resistance Ra, and we have a constant Lv, which is the latent heat of vaporization. Note that Lv is not a true constant in that it can vary with temperature. The latent heat flux is also constrained by energy availability and moisture limitations. So what this means is that if there's no water available for evaporation, then the energy transfer to the atmosphere will be preferentially by sensible heating rather than latent heating. However, if there are no moisture limitations, like over a water body, then more energy transfer can occur via latent heating. So moisture constraints are a large determinant of what pathway energy can be transferred to the atmosphere. But what determines those moisture constraints? One of them is the aerodynamic resistance, which is a function of wind speeds, atmospheric stability and surface roughness. Generally, Ra decreases with increasing wind speed, increases with increasing stability and decreases with increasing roughness. It's a quantity that is rarely measured explicitly. However, theoretical estimates for different surfaces show that the Ra can have quite a large range. It's worth noting that over the land surface, the resistance to moisture and heat transfer does not just consist of this aerodynamic resistance term, but it can include, or does include rather, the soil resistance and canopy resistance, the latter of which includes the stomatal resistance and the leaf boundary layer resistance. So these terms become quite important when considering the linkage between water transfer and carbon exchange. We can summarise a surface energy balance as follows. We start with the incoming and outgoing shortwave radiation, which is essentially just the proportion coming in that is not reflected back to space. Then we have the incoming and outgoing long-wave radiation, where the outgoing long-wave radiation consists of two terms. And together we can sum all of these radiative fluxes to get the net radiation. Following this, we have the energy exchange back to the atmosphere via latent and sensible heating. Note that we haven't really dealt with the imbalance that was raised in the first video. So in the context of the surface, heat is also exchanged by conduction between the surface and the subsurface, which we often refer to as the surface net heat flux, G, in the surface energy balance. G takes on a different meaning depending upon whether the surface is land or water. For land, G is referred to as the soil heat flux and is a function of the temperature gradient and thermal conductivity. The magnitude of G depends upon where you are. For the land surface, it's quite small over periods greater than 24 hours, and for the ocean, it can be large over months to years. So that's it. That's the surface energy balance.